Hello, and welcome to my third lecture for Calculus AB about limits. This lecture is about continuity and one-sided limits. Now, I've actually already addressed one-sided limits to some extent. If you'll remember a couple of lessons ago, we had a series of drawings showing how a limit exists and how it has to approach from the left and the right and get the same value to exist. Well, that's what we're talking about here to begin with. So a two-sided limit exists if the limit from the left equals the limit from the right. And you see the notation for this, and if you'll remember the drawing from the past. And so from that, we build our definition of continuity. So a test for continuity is related to that. The continuity test is that if the limit from the left is equal to the limit from the right is equal to the value of the function, then the function f is continuous at that point x equals c. So we can do that in words. This would be good to copy down. In words, we would say that f of x is continuous at a point if the limit from the left equals the limit from the right equals the value of the function at that point. So let's go through some examples of different types of discontinuities and talk about how that ends up being a continuity and a discontinuity in terms of calculus. So here's some examples of types of discontinuities. First is a hole. Now notice in that case we have a function that has a hole in it right there. And if you notice, if we come from the left and approach that point, and come from the right and approach that point, we end up approaching the same y value. In this case, it looks like it's at y equals 2. There's no scale given here, but you can see it's at the same value. So that's a hole, which is a point discontinuity and removable. So like when you're finding limits analytically and you factor and cancel, that's when you're removing the discontinuity, you're actually removing the hole. Okay. The next type of discontinuity we want to talk about is a jump. So in this case, if you come in from the left, we're approaching what looks like to be 2. And we come in from the right, it looks like we're approaching 1. So the limit from the left is 2, where the limit from the right is 1. So the single-sided limits exist, but the two-sided limit does not exist. Okay. Then there's also an infinite discontinuity. In this case, as we approach this value, let's call it c, if we approach c from the left, the function is going up to infinity. If we approach c from the right, the function is also going up to infinity. But since that's not an actual number, it's another form of the limit not existing. So again, the limit does not exist. Need a little darker pen here, make that a little wider. So that's an infinite discontinuity. Okay, let's do some examples of how we deal with continuity in calculus. So in this case, they want us to discuss the continuity of the following functions. And in a way, they're almost asking us to do something backwards. We really wanted to discuss the discontinuities. That's how we'll address the continuity of the function. So if you see on that function, if we were to cancel out the why this isn't, excuse me. Don't know why we're not getting a, there we go. So if we cancel out the x's, that's a removable discontinuity. So we'll say we have a removable discontinuity, we'll abbreviate, at x equals 0. Because when x is 0, we'd have it divide by 0 error. Okay. Meanwhile, we have an infinite non-removable discontinuity at x equals 7. All right. So because when x would be equal to 7, then the function would blow up and head towards infinity. So that's how we'll talk about the continuity of the function. So we'd say that the function is continuous for all values except x equals 0 and x equals 7. Okay, so that's how you address that. a little easier writing on paper than it is writing on this little board here. But let's go on to the next one. Okay, they want us to discuss the continuity again. So again, this is a polynomial on the top and a polynomial on the bottom. And so roughly, normally that will give us a continuous function, except for possibly any points where the denominator is equal to 0. So if you factor the denominator, I like to just do it right below it. That factor should be, I think, x minus 5 times x plus 2. And the top is going to factor to be x minus, or x plus 3 and x minus 2. So in that particular case, none of them cancel out. Let's see, did I get those done right? Yeah, x plus 2. This one's also x plus 2. So it'd be interesting to have this be a plus 6 instead of, or a minus x instead of a plus x. So we'd actually get one to cancel out. But in this case, we have two discontinuities, x equals 5, x equals negative 2, and both of them are non-removable. So we'll say g of x is continuous for all values of x except x equals 5 and x equals negative 2, where we have infinite discontinuities. Okay, so that's example 2. All right, let's move on to example 3. Now, example 3 is a different type of function. Now, notice this is a piecewise function. So it's piecewise linear up here for the x equals less than 1, and it's actually a quadratic for x greater than 1. So you notice that both of those are continuous on their own domains. So we'll say the function is continuous for all real numbers. Except for now we need to see, is it continuous where, actually we'll finish that sentence. The function is continuous for all real numbers where x is not equal to 1. Okay, now we don't know if it's continuous at 1 or not. I should have checked that before I started writing the sentence. So what we need to do is we need to take the limit of h of x as x approaches 1 from the left, and I need to take the limit as x approaches 1 from the right. Okay, so for the left, that would be less than negative 1, so that means it's going to be equal to, or not less than negative 1, less than 1. 2 times 1 plus 1 is equal to 3. All right, from plugging into this one, you're going to put in 1 squared plus 1, because it needs to go in the bottom one, and that's equal to 2. So notice the limit from the left does not equal the limit from the right. So, since the limit as x approaches 1 from the left does not equal the limit as x approaches 1 from the right, the function is not continuous at x equals 1. Okay, so that therefore it makes this statement correct. So all this information down here was backing up the statement we made saying it's not continuous at 1. I was meaning to say that we know it's continuous for everything but 1, and so then we need to test that. So we tested at 1, and we found it indeed was not continuous at that point. If we'd had like x equals 2, so when x is 2, that would be 4 plus 1 is 5, and this would be 4 plus 1 is 5. So if this were breaking at 2 instead of 1, then the function would be continuous for all real numbers. All right, so that gives some examples of checking for continuity, and I'm going to have another video coming up for the intermediate value theorem. Thanks for listening.